Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on February 6, 2026, about 4 days ago. It demonstrates that applying sparse autoencoders to audio models enables effective feature steering, reducing Whisper's false speech detections by 70% with negligible accuracy loss. The paper is titled AudioSAE, Towards Understanding of Audio Processing Models with Sparse Autoencoders. And as we'll see later, the way these learned features align with human brain activity is quite remarkable. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, to configure the sparse autoencoders correctly, the team first analyzed the balance between model complexity and accuracy. Figure 1 plots the reconstruction error on the vertical axis against the sparsity, or L0 norm, on the horizontal axis. The blue curves represent HuBERT base, while the red curves show Whisper small. We see that error drops sharply at first, but then levels off, meaning that adding more features beyond a certain point yields diminishing returns. Because of this distinct elbow in the curve, the researchers settled on a k-value of 50 to maintain efficiency without sacrificing quality. So, Figure 2 breaks down exactly what these features focus on, tracking specialization across speech in red, sounds in blue, and music in green. The top panel shows frame-level features, which capture local details, while the bottom panel displays audio-level features representing global context. Notice the solid green line in the bottom graph. It spikes dramatically in layers 3 through 6, indicating that Whisper dedicates nearly 25% of its mid-layer capacity specifically to processing music. In contrast, the red line in the top graph shows that speech specialization peaks later, around layer 7, suggesting the model disentangles broad audio types before refining phonetic details. Well, besides understanding what these features do, we need to ensure they are reliable. Table 1 investigates this by quantifying feature stability and cross-model alignment. The top row, labeled with a superscript 2, compares two autoencoders trained on the same HuBERT layer but with different random seeds. The high match counts, reaching over 4,000 in layer 10, verify that the method consistently discovers the same concepts. However, the row comparing HuBERT directly to Whisper shows very little overlap, meaning these two architectures learn fundamentally different representations. So, having established feature stability, Figure 4 tests if they are distinct enough to be removed individually. This graph tracks vowel recognition performance as we delete features, starting with those most vital for the letter A. The blue line shows that recognition of A collapses quickly, hitting 0 after removing about 1,100 features. In contrast, the lines for E, I, O, and U stay high much longer, only dropping after 27% of the features are gone. This proves we can surgically erase one sound, though the large number of features required suggests audio concepts are more distributed here than in text models. Okay, while the previous chart suggested some concepts are distributed, Figure 5 proves that others are incredibly precise. It plots the activation strength of individual features over time, directly above their corresponding audio spectrograms. In the top panel, feature 3470 from Whisper Layer 6 works as a laughter detector. You can see the blue activation dots spike clearly during the laughter at the beginning and end, while dropping to 0 during the spoken sentence in the middle. Down in the bottom panel, feature 4719 shows the same specificity for sneezing, firing only when the sneeze occurs. Alright, having identified these specific features, Table 2 shows how we can use them to fix errors, specifically to stop Whisper from hallucinating speech in noisy audio. The column labeled No Steer sets the baseline, where false positive rates on datasets like Muson reach up to 33%. By applying SAE steering with an alpha of 1, shown in the second-to-last column, they slash these false positives dramatically. Crucially, the bottom row confirms this is safe, as the word error rate on real speech only rises from 5.1 to 5.5. But the final column warns that pushing too hard breaks the model entirely, skyrocketing the error rate to 98%. Wrapping up, two takeaways stand out. Sparse autoencoders successfully decompose audio models into interpretable concepts, and this transparency enables direct model steering. By adjusting specific features, we can fix errors like hallucinations without expensive retraining. This points toward a future where audio AI is much more controllable. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.